So now we're getting into active transport. Remember, up until this point, the forms of transport we've talked about do not require any energy input from the cell. They just happen naturally. But active transport requires energy input. It's going to cost us something to make something move. So active transport requires energy to move molecules across the membrane because we're moving from a low solute concentration to a high concentration. So we're going upstream basically. Think of passive transport as sitting in an inner tube just going with the flow down a river versus active transport being where you're trying to swim against the current upstream. If you're lazily floating down the river, you don't require any sort of input from yourself. You can just float on down. But if you're trying to swim against the current up the stream, you're going to have to expend a lot of energy and you're going to get tired. So think of that comparison when you're trying to compare these two. So all we're doing here is we're going to basically try to take those solutes and we're going to try to consolidate them on one side of the membrane in a higher concentration. So this is going to make the membrane side more concentrated rather than less concentrated. We're fighting against equilibrium in this point. So active transport, we're moving molecules against, not with, their concentration gradient. Now, why would we bother doing this? Why would we expend energy to move things? Well, it turns out that by organizing the solutes so that we have a high concentration in one area and a low concentration elsewhere is actually really important for us to do certain jobs within our cells. So we're not doing it just to spend energy for no reason. Right? We're doing it because there's a certain task that requires a very high, like an unnaturally high concentration of ions or solutes on one side in order for a task to be done. Now, there's two ways we can do that. We can do that through like the primary, like straightforward, just active transport or secondary active transport. So one of those forms, like in secondary active transport, we are going to pump, like in this case, a bunch of hydrogen ions on the outside of the cell, and then we're going to use that like artificially high hydrogen ion concentration to help move something else against its concentration gradient. So let's compare the two. In diffusion, we do not require any energy input, whereas active transport does require energy. Diffusion is spontaneous. It's just going to happen without any sort of input from the cell if left to its own devices. Whereas active transport must be directed by the cell. The cell has to actively push forward for this to happen. In diffusion and passive transport, we're moving a solute from a high concentration to a low concentration. Whereas in active transport, we're fighting against that current going from low to high, making the concentrations even more different from each other over time. In diffusion, the goal is to equalize the concentrations on both sides, whereas active transport fights to make the sides unequal, where we're going to push the solute all on one side and keep it off from the other side. Now we're going to get into our last one, which is bulk transport. Now I have this one tied together with active transport because this, generally speaking, is something that requires input from the cell. Bulk transport is when we're moving molecules that are way too big to move through the membrane. So we actually use the membrane to create almost like a little box or a container to pull things in or push things out of the cell. Endocytosis is going to move things into the cell. Think endo is internal and cytosis inside the cell. Whereas exocytosis moves things out. Think exo meaning exit. So this is where we're pushing things from the inside to the outside of the cell. Phagocytosis is a special type of endocytosis where we're actually going to engulf large particles to consume. So we take on this large particle, it's shown here in yellow, and the plasma membrane is actually going to fold in around it, forming a pocket around that particle until finally you can pinch it off. So think of it like if you're putting something in your pocket of your jeans, right? You have the pocket that's serving as part of your membrane, you're pushing it in, and whatever you're trying to bring in, you're putting into your pocket. Now imagine if you could keep pushing through your pocket until the fabric actually pinched off and became its own little pocket of fabric deep inside of your jeans. That's kind of what we're doing here with phagocytosis. That pocket, that pinched off part of the membrane is what we call a vesicle. So it kind of serves as like a container to bring in whatever it is we just brought in. Phagocytosis can be used to bring in large molecules that we're going to break down for maybe an energy source. It could also be something used by the immune system. So when your white blood cells engulf bacteria that are trying to hurt you, they do so using phagocytosis, and many times. Exocytosis is kind of the opposite of endocytosis. We have our vesicle packaged up. It's going to then go and fuse with the plasma membrane and then spill the contents outside the cell. So think of it like if you have something in your pocket, you put your hand in your pocket and you pull the pocket and flip it inside out, spilling the contents outside of your pocket onto the floor. That's kind of what exocytosis is doing. So we've talked about many different forms of transport. We looked at the membrane itself and what the membrane's made of. We looked at the cheap ways for our cell to move things across the membrane, the expensive ways to move things across the membrane, and how we're looking at these things and how they're necessary for the cell to do its daily tasks.